Got a mess this morning. All right. Good morning, gang. Welcome back to MAP2302. Today we're gonna do a handful of things. First, I do want to wrap up the argument we made last time for reduction of order. I want to be reasonable with the time, though, so we're gonna do it kind of quickly. The main thing today, maybe I gotta think about the reduction of order thing. I'll think about it a little bit more while we go through this. The main thing today is constant coefficient linear equations. So there's a beautiful connection between the algebra of polynomials and linear differential operators and a certain kind of high order linear differential equation. And it's going to sort of form the basis, the backbone for most of the equation solving we'll be doing for the remainder of the semester. That's a little bit of an exaggeration, but you'll see what I mean. So here we go. We're also going to talk just a teensy bit about the test. The test went well. Everybody's exam is graded. There were one or two hiccups with people getting booted a little bit early, but we managed those in a way that I think was acceptable, and hopefully that won't happen again. Oh. I apologize. I know I'm looking a little bit ratchet. We had to travel some this weekend to go visit my son's grandma, and it's not left us with a lot of time to clean things up. So let's do this. This, of course, MAP2302, which is differential equations. It's a lecture. And today is the 19th. So you did have a homework due today, just the one from last week. Because we had the exam last week, we didn't saddle you with a bunch of extra stuff. And that is going to put us perhaps a little bit off pace, but we'll manage. Focus, you fuck. Does anybody watch AVE YouTube channel? If you're into engineering, machining at all, I highly recommend AVE. Sorry, the focus, you fuck thing is in my brain from him. Okay, so today I'm going to talk about the exam stats. I always like to share those statistics with you guys so you have a feel for kind of where you stand with respect to the rest of the class, and how I may change exams in the future. Then we're going to wrap up reduction of order, which was what, 4.2, right? That's 4.2, yeah. And the relevant homework was due today. And you know, it really is just that integral formula. But if you need more time on this, I understand we didn't get to work a lot of examples. So if you do need more time, just go ahead and submit an extension request and WebAssign. I haven't checked those over the weekend. Nope, not you. Didn't I have another copy of the browser? Yeah, you. I only have 3 messages here, so I have a feeling not a lot of people have submitted extension requests. But if you do need more time on the reduction of order homework, just let me know. And then the big thing is we're going to cover section 4.3, which is on constant coefficient linear equations. And today there's going to be a focus on constant coefficient linear homogeneous equations. Homogeneous in the sense that the right-hand side is 0, not in the scaling sense. Okay. So first things first, the statistics on the test. They were good. In fact, this is probably the highest scoring test I've seen in a long time, not just here, but like I do a lot of Calc 2, a lot of Calc 1, a lot of Honors Calc, and I haven't seen an average above 70 in a long time. especially not 77, which tells me the test may be a little bit too easy, maybe a little bit too easy. But if I'm honest, I feel pretty comfortable with it. I don't have a problem with this distribution. The distribution looks good. This is what an honest distribution usually looks like. And the individual problems were about where I would expect them to be. Some of the true false were perhaps a little bit tricky, but I think you can sort of reason your way to the answer with any of these, even if you're having a bit of a hard time. The two questions that seemed to give people the toughest time were this guy and this guy, which I did not intend to be hard questions, but I think the subtleties in here are what got us, just remembering the definition of homogeneous, I think made things a little bit challenging, because here we're talking about a function, not a differential equation. So I'm not asking, is a differential equation homogeneous? And I think a few people lost points on that, although I did try to grade it gently. If you took this function and tried to somehow relate it to a differential equation and then showed that the component functions maybe are homogeneous, I tried to give you credit, especially if you showed accurately that the component functions would be homogeneous. However, there is no differential equation here. There isn't even an implied differential equation, like saying this is equal to dy dx is not the same thing as what I'm asking here. But we already went over the solution to this. And this guy, figuring out whether this is or is not an exact equation. The sneakiness here, of course, is that the dy thing came first and the dx thing came second. So normally you think of the first function as m and the second function as n, but that's not the case here. M is always the thing slapped with the dx, and n is always the thing slapped with the dy. And then this minus sign, you had to distribute this minus. So in other words, you got to put this in the kind of standard form for an exact equation before you can jump in, or at least remember what the standard form is. But a lot of folks did a really good job on both of these. So I feel everything is about where it should be. Make sure you look at the work. So exam 1 stats are fine. Make sure you review my feedback. On your written work. All right, so I take the time to make those comments. So please, take the time to read them and internalize them. There were some things in there I saw, calculus errors, algebra errors, definition problems, all sorts of little things, but nothing that jumped out as like, whoa, everybody got this wrong. So there isn't any one thing I'm going to sit here and harp on. I just want to say, please take the time to review the feedback. All right. I think that's everything. Oh yeah, so I have 2 people who need to take the makeup test. And I have arrangements with each of them. But if you didn't take exam 1 and you haven't made arrangements for the makeup test, you need to go ahead and do that immediately. I'm doing 1 makeup session this afternoon, and I'll be doing 1 makeup session later in the week. So you've got an opportunity this afternoon. If you missed it, you need to do it. If you miss the test and you cannot come this afternoon, then you need to get special permission, of course, as always for a makeup test, but especially for the later one. So if you miss the test, come take the makeup this afternoon, just come by office hours. If you can't come this afternoon, but you missed the test, then we'll have to talk, because today is sort of the last day to do the makeup, unless you're in an extreme circumstance, which is one other individual is. Okay, so where do we want to go from here? I think last time, yeah. So we began with an equation beginning with the equation y double prime plus p of x times y prime plus q of x times y equals 0, we got down to, we subbed, what was it? Y2 equals u of x times y1. Let's call it y equals u of x times y1. So we're looking for another function that solves this equation under the assumption that we had one already, right? y1, where y1 is known to solve. This equation here, which I'll just call star. And we got it down to just looking for my notes, got it down to y1 times u double prime plus 2y1 prime plus py1 all times u prime equals 0. Where we further sub w equals u prime. And then it's that w equals u prime that is really the reduction of order. All right, you're saying if I have a differential equation where there are no u's, just u prime, u double prime, and higher, then I can sub w equals u prime, and that'll knock this from a second order equation down to a first order equation. And then if that equation is linear, which in this case it will be, we can use integrating factors, yielding y1 w prime plus 2y1 prime plus py1 w equals 0. So you can separate variables here, actually. If you think of this as an equation in terms of the variable w, this is separable. So if I write this as w prime as dw dx, then I can rewrite this as dw over w plus 2y1 prime over y1 dx plus p dx equals 0. So the steps are just algebra steps here. Think of w prime as dw dx, multiply through by dx. That means everything here will get a dx. And then divide through by w, divide through by y1. So y1 dw dx, the y1 goes when you divide through, and you get a w downstairs when you divide by w. That's where this w goes. And then if you divide this term by y1 and multiply by dx, you get this. This is all y1 prime. I don't know if you can see the one down there. And this is also a, sorry, this is not a y1 prime, this is just a y1. So we're dividing through here by wy1 and multiplying through here by dx. And that's where we get this. And then you can separate variables here. If you separate variables here, separate variables, integrate, you get that the all right, we'll move this stuff over to the other side. Over here, we'll integrate dw over w, or 1 over w dw. After you kind of reorganize everything, you get the natural log of w times y1 squared is equal to negative integral p of x, or just p dx, plus a constant. So you've got to kind of shove these things over and then integrate on both sides. And that we can rewrite. I'm kind of skipping some steps here, but I don't want to burn a lot of time here, which is equivalent to just exponentiating on both sides. Call it C1 and e to the negative integral p dx, where C1 is C. Right, so you exponentiate on both sides. Then we divide through, and we go back through the substitution. That's W is equal to this over y1 squared. And since W is equal to U prime, U is going to be the integral of this. You can pop out integral done dx. So you can pop out the constant. Oh, sorry, y1 squared dx. And we get another constant from this integral plus C2. And then, of course, remember the formula that we're working with under our assumption here. We're assuming that my new function is equal to u times my old function, right? So in other words, y2 is equal to y1 times this thing. So that finishes the job. Therefore, y2, which is equal to u of x, this thing, times y1 of x, is equal to this whole apparatus, and we can fudge some of the constants around. If you choose, right, so these constants are arbitrary, and for any choice of these constants, you should get a function that solves. If you kind of strategically make this guy 1 and make this guy 0, then the formula simplifies a little bit, and we get, so I'll write the y1 out front, times the integral e to the negative integral p dx divided by y1 squared dx here, by choosing C1 equal to 1, C2 equal to 0. And that's the formula that you guys have been told to use in your homework when you want to solve an equation by reduction of order. It's only useful for finding a second linearly independent solution given a first. Only applies to second order linear equations. So it's not really the most badass thing in the world. It's kind of a pain. It's a big formula. There's not a lot of insight, even if you understand the derivation here. At the end of the day, it's not something that you want to go through for each problem. So you do end up just like writing down this formula or using this formula. And nobody really likes it. And nobody really likes something that is just memorization. However, it's reasonable practice, kind of forcing yourself to be careful. The big thing for today, oh, I'll say one other thing before we leave here. Remember, we chose to take C1 to be 1 and C2 to be 0. If, for whatever reason, things work out nicer with other choice of the constants C1 and C2, here's maybe the one place where there's room for a little critical thinking in this section. You can. right? You would be free to choose C1 equal to 5 and C2 equal to pi if you wanted here. And there are some instances where choice of constants can make the algebra a lot nicer. These are just the constants that kind of make the formula look prettiest. All right, so that's the formula for your second solution, assuming you already have the first. And by design, they will be linearly independent. So if you have y1 as a solution to a linear second order equation, you can be 100% confident that once you cook up this y2, you're going to have all the solutions. Because remember, one of the big things that we learned from the theory last week is that an order n equation, linear equation, always has n linearly independent solutions. So once you've found 2 linearly independent solutions for an order 2 equation, you're guaranteed that that's all of them. All right, I'm not going to beat this to death. I am satisfied with this section. I don't find it entertaining or fun to work with. It's just a formula. You do have to learn it. You got to get comfy working with it. If you need more time on the homework, again, you can submit an extension request. If you'd like to work problems, you can come by office hours. We can do examples, but we're just plugging in and integrating. That's all. All right. So next up for us is section 4.3. And in section 4.3, we are going to learn some new shit. This is titled Homogeneous Linear Equations with Constant Coefficients. So I've alluded to these classification schemes a few times throughout the semester. That constant coefficients is kind of one of those boxes that we like to sort these equations into. Within linear equation, right, kind of biggest is PDE, ODE. We live all in ODE land. Within ODE land, you've got like linear and non-linear. And then within each of those, you can talk about homogeneous, non-homogeneous, right? Like right-hand side 0, right-hand side non-zero. And then within each of those, you can talk about variable coefficient versus constant coefficient. We're kind of taking the nice path all the way down the right side of that tree, where the equations are ordinary differential equations, they are linear, they are homogeneous, and they are constant coefficient. This is as nice as they get. Once you step outside of first order stuff, this is as nice as they get. The big idea here is that for equations of this sort, we can assume the solution to be exponential. That's the big idea. So let's go ahead and say it. Big idea. If an ODE is this, right, linear, constant coefficient, homogeneous, then we can assume a solution to be of the form y is equal to some constant times e to the x. That's the idea. I'm just going to say not e to the x, e to the, let's say, mx. So what we're going to do is we're going to find solutions of this form, slap them each with constants, and then glue them together. Remember the theory from linear equations? Once you've found a handful of solutions that you know are linearly independent, you slap each one with their own constant and add them up, and that will be your general solution. The homogeneity here is important. The right-hand side does need to be 0 for this to work out because of the way exponential functions interact with equations equal to 0, right? And particularly, you know, this thing will never itself be 0. And you know that derivatives of these things are polynomials times those things. this is okay. So let me go on here a little bit, because y prime here would be m e to the n x y prime prime. If I differentiate this with respect to x again, I get m squared e to the mx, and so on. So when a linear operator L equal to, I'm going to write these as constants now, so I'll call this an d to the n plus an minus 1 d to the n minus 1, all the way down to a1 d plus a0, where the an minus 1, a1, a0 constant functions. When a linear operator like this, where these are constant functions, is applied to y equals e to the mx, we get, well, think about it. The first derivative is just m e to the mx. The second derivative is m squared e to the mx, and so on. The third derivative would be m cubed e to the mx. We get L acting on y is equal to this piece acting on y, which would be an times m to the n times e to the mx, plus this piece acting on y, which would be an minus 1 m to the n minus 1 e to the mx. And it goes all the way down like this. So you get to this piece acting on y, which would give you a1 m e to the mx plus a0 acting on y. There is no d there. That's just a0 e to the mx. And you can factor out the e to the mx, right? That is a term that shows up everywhere here. E to the mx here, e to the mx here, e to the mx here, e to the mx here. So this will give us e to the mx times an m to the m plus an minus 1 m to the n minus 1 plus all the way down to a1 m plus a0. So you take a linear differential operator with constant coefficients. You know that gives you a differential equation that is linear and constant coefficient. We're assuming the right-hand side is 0. So I'm trying to solve L acting on y equals 0. So I need to set this equal to 0. What's special about this is a detail from your pre-calculus class about polynomials that you may or may not remember. I'm going to say, therefore, L acting on y equals 0 if and only if, well, this thing is equal to 0, right? E to the mx times an m to the n plus n minus 1 m minus 1 plus blah, blah, a1 n plus a0 is equal to 0. In other words, a function of this form is a solution to the homogeneous linear constant coefficient ODE if and only if this equation is true. Now, this is an algebra equation. That's the miracle. In fact, this piece is never 0. For any choice of m or x, right? E to some shit cannot ever be 0, even if you allow for complex numbers. Exponentials are always non-zero. So this has to be 0. And this is where our theory from last week is going to save our bacon. What kind of object is this? The equation 2 star. This guy. Does that look familiar? Has anybody seen something like this in a definition in pre-calculus?
Isn't that just a series?
Well, it's finite in length. So it looks like a power series, but it's finite in length. What do we call those? Power series are infinite versions of what?
Sequences?
And a sequence is a list. There's no addition in a sequence.
That's what I was thinking, just a standard series.
Yeah, it's closer to a series than it is to a sequence, but it's not either of those things. Think way back. This is a word you knew long before Calc 2.
Polynomial?
Yeah, it's a polynomial. What's the degree of the polynomial?
N?
Yeah. Okay. What do we know about polynomials of degree n? How many roots do they have, or how many solutions does this equation have?
N solutions.
Good. I should say as a polynomial equation. A polynomial is the object on the left. Polynomial equation of degree n, which we know from the fundamental theorem of algebra. We know from the fundamental theorem of algebra, has how many solutions? N of them, right? Okay, well, this is a big deal. Remember, we said that a linear equation of order n should have n solutions. If you've got n linearly independent solutions, then you know that that's all the solutions to the equation. The equation in question is equivalent to L acting on y equals 0, which is itself equivalent to this algebra equation, which is itself equivalent to this polynomial equation, which we know has n solutions. The solutions here are values of the variable m, right? The variable in this polynomial is m. N solutions. So degree n, which means we've got n different values for m that we can plug into this function y equals e to the mx. Each one of those is a different solution to the differential equation. And solutions. Hence, we have n solutions to the order n linear ODE, which means it must be all of them, which means that must be all the solutions. So in other words, by assuming you have a solution of the form e to the mx, we're able to prove that all the solutions have to be of the form e to the mx, because the homogeneous linear constant coefficient ODE reduces down to a polynomial of degree n And each solution, each root of that polynomial, each solution to that polynomial equals 0, yields a different function that solves the differential equation. That's a big deal. There's a few subtleties that we should address before we move on. First, are those solutions linearly independent? How do I know those solutions are linearly independent? Is e to the 2x linearly independent from e to the 5x? The answer there, I'll just spoil it for you, is yes. Yes, they are. They're linearly independent. You can check 2 at a time that exponentials with different powers are linearly independent because they're not constant multiples of each other. You can show that through power series. I'm not going to do it. So I'll just tell you that, yeah, if you have two different values for m here, like e to the 2x and e to the 5x, those are linearly independent. All right, I won't make you go through that. I think it might have been in the last homework set. Other things, this only works if the equation is homogeneous. Right, this only works if you're setting the right-hand side equal to 0, because those are the only linear equations that we know have exactly n solutions. If you have a more complicated right-hand side, there will be a particular solution. We talked about that also, right? YC and YP. The YPs that you get if you have a non-homogeneous equation, they don't count in this list of n solutions. So homogeneous linear differential equations have as many solutions as the order. And then if this right-hand side is non-zero, you'll have to find particular solutions, but we're going to address that later. Your book comes into this in a very gentle and what I feel is a slightly silly way by talking about the second order equations. They don't trust you guys to do this, but I trust you guys to do this. And in practice, most of the equations we're going to solve will be second order because it's harder to work with polynomials of degree 3, 4, 5, 6. You may know that while there is a quadratic formula, there is a cubic formula, there is even a quartic formula. There is not and cannot be a quintic formula. There is no formula for the roots of a degree 5 polynomial in terms of the coefficients. So solving an equation like this, if n is 5 or larger, can be really, really hard. In some special cases, we can do it, but in general, it's quite hard. So second order equations form a nice prototype. Okay. I am going to look at second order equations kind of on their own a little bit because it's easier to break things down for them. But before we do any of that, I want to talk a little bit about something from Calc 2. All right, let me back up a bit. So that equation that I labeled 2 star is called the auxiliary equation. It's 2 L's or 1, I think 1. Auxiliary, I'm gonna look. Yeah, equation. For the differential equation. There's a lot of word soup here. It's the auxiliary equation for the linear homogeneous constant coefficient ODE. Polynomials have solutions or roots that come in certain ways. You can have n distinct roots, right? All different real numbers. You could have repeated roots, right? Roots that come in higher multiplicities, like m-1 quantity squared that has a repeated root of m equals 1. Or you could have complex conjugate roots. So I need to show you some theorems from algebra. First, the fundamental theorem of algebra. I referred to this earlier. This states that a polynomial of degree n has n roots when counted with multiplicity. That's the vibe. And you can factor the polynomial to find the roots. And the roots come from factors. All right. Another theorem, I don't think this one has a name. Another theorem states every polynomial can be factored into linear factors and irreducible quadratic factors. So linear factors, remember these, correspond to real roots. And these irreducible quadratic factors correspond to complex conjugate roots. Complex conjugate root pairs. Right, like x minus 3 is a linear factor, and it corresponds to the real root 3. X squared plus 1 is an irreducible quadratic factor, and it corresponds to the roots 0 plus I and 0 minus I, which are complex conjugates. So, if we're thinking about auxiliary equations as polynomial equations that we want to solve, i.e. we want to factor, to find our solutions, e to the whatever times x, where the whatevers are these roots, it's useful to know that there's only these cases, right? Every polynomial can be broken down into linear factors and irreducible quadratic factors. This is actually quite hard to prove. I can give you some polynomials of degree 4 that are fucking hard to do this to. Take x to the 4 plus 1. Enjoy. Surprisingly hard to find the corresponding irreducible quadratic and linear factors there. They exist though. The fundamental theorem of algebra just guarantees that you can factor shit and that there will be n roots. The big deal is the second theorem. These guys are not so bad to deal with as long as they're not repeated. So maybe one final thing which I'll just call here a fact. Both linear factors and irreducible quadratic factors can show up repeated or non-repeated, meaning multiplicity strictly greater than 1 or non-repeated. Multiplicity equal to 1. And it turns out that the repeated factors can cause us a little bit of a headache, because obviously if I have e to the 2x and e to the 2x as two of my solutions, those are not linearly independent. So in the case of a repeated linear factor, I will show you how to cook up your second linearly independent solution. it basically comes from what you think it comes from. It comes from the reduction of order bullshit that we did last time. If you have a repeated complex root, I'm not going to deal with that. I'm not going to deal with that right now. We may encounter that this semester. I don't believe your book even touches it. I didn't learn about that stuff until I was in graduate school. I didn't learn how to deal with differential equations that have repeated complex roots until graduate school. I don't believe it's in your text. Okay. One more theorem, and then we can actually get to solving some stuff. This one is also special. This is usually called Euler's formula. This says, I'll just say it, e to the I theta is the cosine of theta plus I times the sine of theta, where theta could be any number, real or complex, and I is what you think it is. It's the square root of -1, although mathematicians would prefer to say I squared is equal to -1, the complex unit. The proof of the theorem at the bottom there, so we've got a handful of theorems on the page, some of which are very hard to prove. These are hard to prove. In fact, all the theorems on the page are hard to prove right now. This one I prove at the end of Calc 2, if there's time, using power series. It's not too bad. I'm just going to say that. What you do is you write down, okay, e to the I theta, that should be the sum from n equals 0 to infinity of I theta to the n over n factorial. And then you write out the series and you look at the powers of I, and you realize that the powers of I cycle every 4. And after doing some work and rearranging and some head scratching, what you get is the sum from 0 to infinity, theta to the 2n over 2n factorial with a -1 to the n, plus I times sigma n from 0 to infinity, -1 to the n, theta to the 2n plus 1 over 2n plus 1 factorial. And these are the series for cos theta plus I times the series for the sine of theta. So all the work is in the ... dots. I think what I'll do is probably post a little video. This is something I love doing at the end of Calc 2 when we have time. Those of you who took it with me last semester, I don't think we had time at the end to prove this. So I'll go ahead and post like a video or something where you guys can see the proof. It's not hard. You just have to write this series out and then look at the terms that end up being real or imaginary based on the power of I, and then reorder the terms. I'll tell you, if you want to try this on your own, the trick is that I to the 0 is 1, I to the 1 is I squared is -1, I cubed is -1 times I, which is -I, and then I to the 4 is equal to 1 again, and it loops. So I encourage you to prove this yourself. If you've never done it before, it's a really good exercise in power series. We will be using power series at the end of the term. And we'll be using this theorem here. So the theorem, this is what we use when we've got some complex roots. All right, if I have complex roots, then those will correspond to exponentials with complex powers, which themselves correspond to sines and cosines. Believe it or not, this is a true statement. I don't want to burn too much time just trying to blow your mind explicitly with this statement. If you plug in pi for theta, you get that famous equation e to the I pi plus 1 equals 0. You get e to the I pi And this is -1, and this is 0. So e to the I pi equals -1, which is the same as saying e to the I pi plus 1 equals 0. You can learn all sorts of fun things with this. You can take the natural log of I. You can take the natural log of -1. You can do all sorts of fun shit. But I'll let you play with that. It's a beautiful theorem. If you haven't played with it, you really should. But that's not for this class. So how do we use all these things to solve differential equations? Well, you write down the auxiliary equation, the polynomial, and you factor that polynomial. If you're lucky, you get non-repeated linear factors, which correspond to simple exponential solutions. If you're unlucky, you get some combination of those and these, but hopefully still not repeated. If you're unluckier, then you get some repeated ones of these and maybe some non-repeated ones of these. And for the repeated ones of these, you take the first guy, and then you use the reduction of order formula to cook up the others. So let me outline the strategy. I'll hold here for just a second. Are there any questions on the theorems? Where? So the strategy for solving these things, which are homogeneous, linear, constant coefficient equations. First, cook up the auxiliary polynomial. In other words, assume y is equal to e to the mx. 2, factor the auxiliary polynomial to find roots. And then 3, solutions depend on the following cases. Case 1, distinct real roots. Say M1, M2, up to N. Right, if you've got M distinct roots to the auxiliary polynomial, then your solution is y equals C1 e to the M1x plus C2 e to the M2x, and so on to Cn e to the Mnx. Like we said, just what you think. Take linear combinations of those exponentials. Case the second, repeated real roots. Here we're going to use reduction of order. So I need to pick some notation for this. Say M1 is equal to M2 are both roots. So I've got two roots. I've got one root that shows up twice, like m minus 1 all squared means 1 is a repeated root. In that case, one of your solutions, let me call this say M1 is equal to M2. Let me call it K. So I have a symbol that represents both. Then your solutions, one is what you think. Y1 equals e to the kx. And y2 is going to come from reduction of order. So this is e to the kx. I'm just plugging into that formula times the integral of e to the 2kx divided by, oh yeah, of course. So if you plug into that formula, e to the integral of p there is the same thing as y1 squared. So this, I say by reduction of order, so this integrand here is 1. So you get your e to the kx times integral of 1 dx, which is just x e to the kx. And then you put them together. So y would be equal to c1 e to the kx plus c2 x e to the kx. If you have higher order repeated roots, like a root of multiplicity 3 or more, then things get a little bit harder. But you can sort of churn one out from the other using this process. You just have to take your reduction of order process and apply it recursively. Again, I won't give you that stuff. Just focusing on the basics here. The third case, which is the cool one, you have complex roots, non-real complex roots. So n is equal to, let's say, triple Q's. Yeah. Alpha plus and minus I beta. So remember, they always come in complex conjugate pairs. It's like 1 plus 3i, 1 minus 3i. Each one of those pairs, via Euler's formula, will yield a combination of exponential and trigonometric functions. So here, I'm going to just tell you what the solutions are. Your solutions here will be e to the alpha x you can put it all in one thing, I guess. Yeah. C1 e to the alpha x cos beta x plus C2 e to the alpha x sine beta x. And this comes from the Euler formula. A little quick because e to the alpha plus I beta times x is e to the alpha x plus I beta x, which is e to the alpha x times cos beta x plus I sine beta x by Euler's formula. And then you take the real and imaginary part, and each one gives you a real solution. The reasons for that are just algebra juggling. It's really not that exciting. Again, I can show you the details there if you really want. Because these come in complex conjugate pairs, you would have one of them that looks exactly like this, coming from the alpha plus I beta, and the other one, let's show you. The other one is coming from alpha minus I beta. So this would be e to the alpha x minus I beta x, which should be e to the alpha x times cos beta x. And then this minus right here would give me a sine of negative beta x, but since sine is an odd function, you get minus I sine of beta x. And then if you combine these, if you add them, you'll get 2 e to the alpha x cos beta x. And if you subtract them, you'll get, let's see, if you subtract them, the cosines will go away, and you'll get just the pure sines. So you take each one of those on their own, linear combinations. That's the idea. Subtracting these, you would get 2i sine beta x, e to the alpha x times 2i sine beta x. So you end up with e to the alpha cos beta and e to the alpha sine beta stuff. And those are your linearly independent solutions coming from these roots. Those are the three cases. That's it. All right, so you find the auxiliary polynomial, factor the auxiliary polynomial, and then depending on which of these cases you're in, you just write down the appropriate solution. So let's get to it. Let's solve some equations. Are we ready?
Can I have 1 second?
Sure. We'll here for just another minute or two. Maybe it's worth it to box these.
Okay, I'm good. Thank you.
All right. So each of those cases yield distinct solution sets. And of course, you could have a combination of these. Maybe I have 3 distinct roots, 1 root that is repeated twice, and 1 set of complex conjugate roots. And then you would just sum all of those things. All right. So let's pick a differential equation to solve. How about 2y double prime minus 5y prime minus 3y is equal to 0. All right. The equation is linear. It is homogeneous. The right-hand side is 0. And all of the coefficients are constant. What's the auxiliary polynomial? All right, I'll write it out this time. If we assume y is equal to e to the mx, then y prime is m e to the mx, and y prime prime is m squared e to the mx. So we get 2 times m squared e to the mx minus 5m e to the mx minus 3 e to the mx. And that's all equal to 0. So 0 on the left, just to make life easier. Factor out the e to the mx, and you get 2m squared minus 5m minus 3. So notice the relationship between the primes and the powers of m. You really can just write down this auxiliary polynomial right away. You don't actually need to go through this process. Yeah, 2y double prime, oh, 2m squared, minus 5y prime, oh, minus 5m, minus 3y, it's just minus 3. It's like the primes are powers. Okay, so I don't care about this. This is never equal to 0. I only care about this, so I need to factor this. So the auxiliary polynomial, call it p of m, is 2m squared minus 5m minus 3. So we need to factor that. Who can tell me how to factor that? Fun trip back. You use the AC method. So you compute AC, where these are like the things from ax squared plus bx plus c. So a times c here is 2 times negative 3, which is negative 6. And then you find two numbers which satisfy two conditions. One, they have to multiply to AC, which in this case is negative 6. And two, they have to add to B, which in this case is negative 5.
Wouldn't it be 2m minus 1 and then m plus 3?
That sounds right. Yeah. So the game here, I'm gonna walk through this just for anybody who forgets it. Here, those two numbers that multiply to negative 6 and add up to negative 5, those are negative 6 and positive 1. So I'm going to write this as 2m squared plus m minus 6m minus 3, because the last step here is to factor by grouping. You rewrite b as the sum of the two numbers, and you factor by grouping. All right, so in case you forget how to do this, this is how you factor quadratics that don't have lead coefficient 1. From the first group here, I can pull out an m, and I get 2m plus 1. From the second group here, I can pull out a minus 3, and I get 2m plus 1. So this is m minus 3 times 2m plus 1. In other words, the roots are m equals 3 and negative 1/2. Therefore, solutions, or the solution, is y equals c1 e to the 3x plus c2 e to the negative 1/2 x. And that's it, job done. Not too bad, right? Really all comes down to those factoring skills that we said would be so important back in pre-calc. Let's try another one. Yeah, let's try. Oh, I guess I should hold here. So questions on how we solved this differential equation, where the auxiliary polynomial came from, how we factored it, or how we got the solutions from those roots. Do I know that this is all the solutions? Could there be others?
Those are all of them.
These are all of them, right? How do I know that?
It's of order 2.
Good. This is a second order ODE, second order homogeneous ODE, and these are two linearly independent solutions. So that has to be all of them. Those sort of questions make really good true-false questions on the test. You may have noticed, right? That's sort of like, what can we say about this? Is this everything? Am I missing something? So I want you to engage your mind when I ask those questions. The more you think about and are willing to answer those, the better tests will go. Okay, let's try something a little different. Let's see if we can solve y double prime minus 10y prime plus 25y equals 0. So again, linear, constant coefficient, homogeneous. So it's all about finding that auxiliary polynomial. This time, I don't want to write everything out. I want you to just tell me the auxiliary polynomial. Call it P of M, P for polynomial. What is my auxiliary polynomial?
M
M
squared.
squared is 10m plus 25.
Very good. Okay. So I need to factor this. Here, the lead coefficient is 1. I'm sure everybody can tell me how this factors. How does this factor?
M minus 5 times N minus 5.
Yeah, good. Which is the same as M minus 5 quantity squared. So I don't have distinct real roots. I've got a repeated root. I've got a root of multiplicity 2. So what are my solutions? I'll have,
E to the 5x and x e to the 5x.
very good. That's it. Right, not bad. Not bad at all. Questions on this one? So you don't need to go through the reduction of order formula here. We just use the reduction of order formula to get the result. All right, one more example. Check time real quick, see where we're at. 10:58. We got plenty of time. Okay. One more example. Let's look at y double prime plus 4y prime plus 7y equals 0. So here, my auxiliary polynomial P of M is m squared plus 4m plus 7. And there's a quick way to check if your polynomial is irreducible. If you're having a hard time factoring, like for example, here I'm hunting for two numbers that multiply to +7 and sum to +4. You're gonna have a hard time. There certainly are no integers. You might think, oh, maybe there's some fractions that would work. I can't find them. You can check for irreducibility. Check irreducible. Using the discriminant. That's that b squared minus 4ac thing. If this is negative, then your polynomial is irreducible. If this is strictly positive, then your polynomial factors over the reals. And if this is equal to 0, then your quadratic has a repeated root. So in this case, I've got 4 squared minus 4 copies of 1 times 7, which is 16 minus 28, which is definitely less than 0. In particular, it is negative 4 plus 8 is negative 12. So the roots. So P of M is irreducible because b squared minus 4ac is less than 0. But we still have to find the roots. And that just means you're going to use the quadratic formula. Or you can complete the square. It's up to you. I'll use the quadratic formula because I think that's what most people will do. That's negative b plus and minus the square root of b squared minus 4ac over 2a. And the discriminant, the piece under the square root, we've already calculated that. So I'll just plug that in. That's negative 12. B is 4. So this is negative 4 plus and minus the square root of negative 12 all over 2. So that's negative 4 plus and minus. The square root of negative 12 is kind of interesting. 12 is 4 times 3. There's a negative under there, so that's I times the square root of 4 times 3. And that's 2 times the square root of 3. All 2. And then you can factor a 2 out from the top, and you get negative 2 plus and minus I times the square root of 3. So your alpha is negative 2, and your beta is the square root of 3. So what does that mean our solutions are? C1 e to the alpha times cos beta, so that's, sorry, e to the alpha x, so that's e to the negative 2x times the cosine of the square root of 3x plus C2 e to the alpha x times the sine of beta x. And those who took Calc 2 with me may remember me talking about how important damped harmonic oscillators are. Well, here's why. All right, this is your damped harmonic oscillator. You've got an exponential, which is decaying, times a pure sine or cosine that's oscillating. So this harmonic oscillation is being damped by this guy. And these things show up in a lot of second order differential equations. Interesting natural phenomena. Certain circuits, you'll see this in a lot, like electrical circuits, where you've got like an LRC circuit that causes an oscillation and then some factor that dampens things, like a load or a resistor, extra resistor. That's the game. That's the game. Okay. I'm going to share with you some special differential equations that you should know the solutions to right off the top of your head. And then we're going to look at a couple higher order equations. Any questions on the examples on this page? Okay. 2 equations you really need to know off the top of your head, depending on how much you care about hyperbolic functions, I guess. One equation you definitely should know. If I differentiate sine twice, what do I get? What's the second derivative of the sine function?
Negative sine.
Negative sine. And if you differentiate cosine twice, you get negative cosine, right? So sine and cosine solve y prime prime plus y equals 0. And more generally, the regular harmonic oscillator is the solution to y double prime plus omega y equals 0. This has solutions y equals, say it like this, y equals c1 cos omega x plus c2 sine omega x. Now that kind of curly w is called omega. It's the lowercase Greek omega, and it generally stands for angular velocity. It's related to frequency. The other one, so this guy has these solutions. Also, y double prime minus omega y equals 0. Here, the corresponding polynomial has real roots, but the roots are kind of nice and symmetric. Actually, this should be omega squared here, shouldn't it? Yeah. Sorry. Okay, let me write it like that. Omega squared. Omega squared. This could just be a constant, right? We don't really care what the constant is. This guy gives you regular sines and cosines. This gives you hyperbolic sines and cosines. The hyperbolic sines and cosines are what they sound like. If you, instead of the unit circle, use the unit hyperbola, then do the same thing that you do on the unit circle to get sine and cosine, you get sinh and cosh. Also, if you look at cosh x and you swap the x for ix, turns into cosine. And sinh ix turns into sines. So these are kind of like nice ways to go back and forth between real numbers and complex numbers. They're really beautiful for lots and lots and lots of reasons. But these two differential equations you should recognize immediately, as soon as you see them, especially this guy. This guy I won't beat you up about too much. If you want to write these solutions in terms of e to the x and e to the negative x, I would let you do that, and I wouldn't count off that you don't recognize them as hyperbolic sines and cosines. But this motherfucker, you gotta know. Gotta know him. He's going to show up just everywhere. And anybody who's taking physics has probably already seen it. I hope so. Good physics class. All right. What about higher order equations? So same stuff, linear, homogeneous, constant coefficient. That theorem I gave you that every polynomial can be split up into linear factors and irreducible quadratic factors becomes useful here. So it works exactly how you would think it works. The catch is that you might have higher order repeated factors, right? You might end up with repeated factors that show up, 3 times, 4 times. So here's how we handle that. Let me look at, I'll just show you through examples. Y triple prime plus 3y double prime minus 4y equals 0. The auxiliary polynomial P of n is m cubed plus 3m squared minus 4. And factoring something like this can be kind of tricky. Does anybody remember the rational roots theorem? Anybody here take pre-calculus with me? I don't even know if I've seen other pre-calc classes not cover this, so it scares me a little bit. There's something called the rational roots theorem. It says if a polynomial with integer coefficients or rational coefficients, if P of n has any rational roots, then those must be of the form plus or minus little p over little q, where little p is a divisor of the constant term and little q is a divisor of the lead coefficient. So here I could go hunting for roots of this order 3 or degree 3 polynomial because it's hard to factor, right? Or you could try to factor it by grouping. So if we apply the rational roots theorem, it says that the only possible rational roots here are plus or minus p over q, where p is a divisor of -4 and q is a divisor of 1. So that would be plus and minus, the only divisor of 1 is 1 itself. So that's plus and minus 4, plus minus 2, plus minus 1. Now I'll tell you, looking at this thing, if you just stare at it for a minute, you realize 1 is a root, right? If you plug in 1 for m, you get 1 plus 3 minus 4. But you could go through and check each one of these using synthetic division. That would take forever though, so I'm not going to do that. Instead, there's one approach. Or you can factor by grouping. I think that will work here. I can write P of m equals m cubed, let's see, plus 4m squared minus 1m squared minus 4. Is this going to work? Yeah, I think it will. If I take an m squared out from the first, I get m plus 4. And if I take a, oh, no, this ain't going to work, is it? M squared. Yeah, minus 1. Give me m squared plus 4. Yeah, no dice. All right. Sometimes you can factor by grouping, but not here. Nope. All right, so we're gonna have to do this thing. Like I said, I can tell that 1 is a root, so I'm going to, I can see that m equals 1 is a root. So synthetic divide. The coefficients of this polynomial are 1, m cubed plus 3, m squared plus 0, m minus 4. This is the synthetic division. I bring the 1 down. 1 times 1 is 1. I sum these. I get 4. 1 times 4 is 4. I sum these. I get 4. 1 times, oh, is 1 wrong? Did I do something wrong? 4. No, this has to be a root. Did I skip? Oh, this is a minus 4. Yeah. Okay. 1 times 4 is 4. And this is 0. All right. Which means that P of m, my polynomial, can be written as m minus 1 times, these will be the coefficients of the quotient. If you want, I actually just taught my pre-calculus class how to do synthetic division and all of this, so I can post a link to the video where I go through this with them. But what this tells us is that I've got m minus 1, the factor that comes from this being a root. This is a root because my remainder here is 0. And then these are the coefficients of the quotient. I'm dividing a cubic polynomial by a linear polynomial, so I'll get a quadratic out as a result. and that's m squared plus 4m plus 4. And then I need to work on that m squared plus 4m plus 4. That factors nicely though. That's m plus 2 quantity squared. All right. So what does that mean? It means my roots are m equals 1, and this is multiplicity 1, and m equals -2. This is multiplicity 2. So the solution to the differential equation is y equals c1 times e to the 1x plus c2 times e to the -2x plus c3 times x e to the -3x. Just like that. I'll just say here. Oh shit. This didn't work. Factoring by grouping didn't work. We had to use the synthetic division. That rational roots theorem is kind of the most powerful tool we have at this level to factor polynomials. If you don't remember it, I encourage you to check it out. Okay. What would happen if I had a multiplicity 3 root or a multiplicity 4 root here? Well, I would go x e to the, e to the -2x, x e to the, oh, I'm so sorry, this is a 2. I'm so sorry. I was thinking in my head, C3. If you had a higher multiplicity, you just continue this thing. So like e to the mx, x e to the mx, x squared e to the mx, and so on. I can do a quick example like that if we like, but I want to take a second here and see what you guys feel about this, because there's kind of a lot. Questions on this one?
Yeah, how did you do the possible rational roots, like the p over q?
So you take divisors of the constant term, which in this case, constant term is -4. So his divisors are 4, 2, and 1. And divide that by divisors of the lead coefficient. Now the lead coefficient here is 1. So the p's are divisors of the constant term, and the q's are divisors of the lead coefficient. So you have to form all possible combinations, divisors of -4 over divisors of +1. Now, since the only divisor of 1 is 1, the only possible combinations are +-4, +-2, and +-1, the divisors of the constant term. Now, this is called the rational roots theorem. While I have you all captive, maybe I'll go ahead and reference this often enough. Share this with you. It is something you're supposed to learn in pre-calculus, but I think maybe some pre-calc teachers don't give it the love it deserves. It says if you have in general, you're trying to find the roots of an order n polynomial, a degree n polynomial, then the roots have to be divisors of the constant over divisors of the lead coefficient. In other words, the only rational roots will be of the form p over q, where p divides the constant and q divides the lead coefficient. And then you just have to check. Right, so what you do generally is you come up with a big old list of possible rational roots. Like here I have 6 of them, and then you would check them one at a time using synthetic division until you find somebody who gives you a remainder term of 0. Once you find a guy who gives you a remainder term of 0, you know that x minus that thing or m minus that thing is a factor. These guys give you the coefficients of the quotient, and then you continue trying to factor that quotient polynomial. So maybe before we go, I'll look at one more example where we get to use that. Okay. Oh, here we do actually have a higher ordered repeated complex root. We can look at one of these. I didn't think your book had this in it, but it does.
Professor, just a reminder on the time.
How are we doing? Got you guys till 11:20, right? Oh, we are at time. Okay, then this is where we'll pick up next time. All right, so the next thing we're going to look at is repeated complex roots. Your book does show you how to manage those. It's not that bad. It is more just of the reduction of order thing, and the result is easy to remember. And then it goes on to talk about the rational roots theorem, which we already did. So I'm going to go ahead and post your guys' new homework. It's going to be just, the homework between now and Wednesday is just going to be coming from this section 4.3, where you're solving these homogeneous constant coefficient linear equations. That is it from me then. I do invite you guys to take a look at this if you're not familiar with the rational roots theorem. I think Paul's online notes probably has a thing on this. Yeah, here, let me send this to you in the chat too, so I don't have to try to remember to send it elsewhere. All right, so those two links in the chat will be useful if you forget some of this polynomial stuff from pre-calculus. It's good stuff, and you can practice finding roots of polynomials there.
Professor,
Yes.
I had a quick question. Are you gonna post last week's lesson, like the recording of it?
Yeah, it's
go-
already up. I posted. I'm
Oh.
sorry I didn't get it up sooner, but it is up now. Yeah,
Okay, thank you.
of course. Alrighty. I think I have arrangements for one of you to take the makeup test with me today. If you missed the test, haven't made arrangements, please do that immediately. Otherwise, I will see you guys tomorrow. Have a good day.